All right. Good morning, good afternoon, good evening, whenever you're watching this. Mr. Atterbury, we're going to go over Chapter 2, the PowerPoint for stats, okay, displaying and describing categorical data. So let's take a look at what this chapter is all about, okay? So, three rules of data analysis. Three rules of data analysis won't be difficult to remember. Make a picture, make a picture, make a picture, okay? Things may be revealed that are not obvious in the raw data. These will be things to think about. Important features of and patterns in the data will show up. You may also see things that you did not expect. The best way to tell others about your data is with a well-chosen picture. So remember from chapter 1, we talked about thinking, we talked about showing, we talked about telling. All right, same thing. You can think about your data by making a picture. You can try to look for features and patterns in data, okay, that things that will show up by making a picture, things that you weren't expecting maybe, okay? Last but not least, you can tell others what you found by making a picture. So making a picture, drawing a diagram, making a graph, those kind of things you learned in probably previous classes as well. We'll probably cover maybe some new ones here, but they're used in three ways: to think about what you're doing, to show what you're doing, and to tell others what you've done, okay? So frequency tables, making piles, okay? The way, a lot of times I call them buckets. You'll hear me probably refer to this concept as buckets. But we can pile the data by counting the number of data values in each category of interest. We can organize these counts into a frequency table, which records the totals and the category names. So the best way I like to think about with this data is when you have categorical data, right? This is all for categories, all for categorical data. So if you count up all the things you recorded, you put them into what's called a count, okay, which goes into a frequency table, as you see on the picture here, right? It says first class, second class, third class, and crew. These are all tickets, okay? I believe this problem we're going to see here in a moment has to do with the Titanic, and it wants to know about, how many people from first class tickets or second class tickets or third class tickets or just part of the crew, the people that worked on the Titanic. So you counted up how many people were in first class, 325. Okay, you counted them up. Okay, and it's all organized into a frequency table. When you hear this idea of what's called relative frequency, okay, relative frequency is essentially taking the part divided by the whole, okay, and making a decimal, which you then turn to a percentage. Percentage meaning adding two decimal places, right? So like 0.12 would be 12%. 0.012 would be 1.2%, okay? So first class, second class, third class, and crew, we notice here that instead of giving the raw numbers, we give them as percentages, okay? It's called relative frequency because if you have different things that are grouped together and you have like, let's say all these tickets here, whatever, and we don't quite know if there was 100 tickets sold, 500 tickets sold, 10,000 tickets sold. All we know in this case is like about 14.5 or 14.77% were first class. Now, if we compare that to something maybe similar, maybe they had more or they had less, but you want to compare their first class tickets versus those first class tickets, maybe other one has a higher percentage of first class seats available, or maybe it's less. Okay, that's why it's called the relative frequency table. Making piles continued. Okay, so both types of tables show how cases are distributed across the categories. They describe the distribution of a categorical variable because they name the possible categories and tell how frequently each occurs. Okay, and it says a little pro tip here: relative frequency is just a fancy name for percent. Okay, relative frequency. Bleh. Relative frequency is just a fancy name for percent. Okay, try not to forget that. So what's wrong with this picture? Okay, you might think that a good way to show the Titanic data is with a display that looks like this, okay? There was more crew members than third class ticket holders, and there was more, looks like, first class ticket holders than there was second class ticket holders. But what is wrong with that picture? Okay. The general rule is what's called the area principle. Okay. The area principle states that the area occupied by a part of the graph should correspond to the size of the value it represents. So sometimes when you have these pictures that are odd shapes, you're using like a picture of a ship to represent like a distance on like a bar. Okay. Having that picture kind of distorted looking can kind of distort your thinking or your perception of what that actual value represents. Okay. So by just making everything the same, just make a bar graph. Okay, just use nice, easy, simple to read and understand shapes instead of trying to do weird stuff. Okay, try to, when we look at each ship, we see the area taken up by the ship instead of the length of the ship. Because what we really want to look at is not just the size and the shape and the area that it represents. We want to look at just the bar graph and how far it goes out. Like you see on the bottom one, it says the first class goes a little above 300. The second class is that a little less than 300. It's a little hard to tell. Like, where is the number? Like, yeah, that boat or that ship looks a little smaller, but it's just best to obey the area principle and just make bar graphs, or just make easy to see and understand graphics and displays. Okay, to think, show, and tell your data. You don't want to go too crazy with making things too flashy with big pictures and big diagrams that have all these weird shapes, okay? Keep it simple, all right? That's the area principle. Bar charts. A bar chart displays a distribution of categorical variable. One more time. You have a categorical variable, you want to display it, use a bar chart, okay? So what's so big right here on a bar chart, okay? They're usually spaced apart to make the graph more readable. So you don't have to have the bars spread apart, but generally speaking, with a bar chart, you have frequency, and the frequency can go up and down, or the frequency can go left and right. It's generally up to you and your preference. I personally like to do the frequency up and down, and that's the way I show it with pretty much all of my examples. Okay. And then the categories themselves, okay, not the frequency, but the categories that you count to find the frequency, they'll then go on the other axis, so left and right. Now, in this case, we see first class, second class, third class, and crew. And then it has a bar graph, and they're slightly separated, but they're nice and clean, the same color, nothing too crazy. And it's a lot easier to read. This shows first class is somewhere between 200 and 400, probably looks a little above 300. Similar to second class, looks a little less than that. Third class is what, close to 600-700 maybe, and then the crew is over 800. So it's a lot easier to display data that looks like in a bar graph than in this. This is just a hot mess. Okay, this like violates the area principle, and this is just a bar chart. Just do it. Okay. Once again, only works for categorical variables. Quantitative variables have a very similar, but it's a different kind of chart, okay? Because you don't do frequencies and counts with quantitative numbers, because you actually have averages and things. With categorical variables, you can't have an average ticket. Okay, it doesn't quite make sense. They have their own kind of graphical displays, and you got to understand when to use which one for each kind of data type, okay? This is very similar. A relative frequency bar chart is the same thing. You should notice the chart looks exactly the same, but the left-hand side changes, okay? So replacing the counts with percentages in the ship data, okay? It doesn't look much different, does it? Okay, it shouldn't. It should look exactly the same. The difference is whoever created this, they took the raw numbers, right? Made the percentages, like here, 14%, 12, almost 13%, 32, 40%, right? And that's what we got there. Not too bad. Pie charts, okay? Pie charts look generally pretty good with categorical data as well. If you have categorical data, You can usually never go wrong with a pie chart. However, a pie chart, if you have like a lot of bars, like I would say maybe like more than like 5, okay, 5 might be kind of cutting it, but you don't want to have too much information to try to read and understand. I would say if you have a categorical data set with just a handful of categories, I would probably personally put it into a pie chart. I like the way it looks. I think it's really super easy to read and compare the data. Okay, when you're interested in parts of the whole, a pie chart might be your display of choice. Pie charts show the whole group of cases as a circle. They slice the circle into pieces whose size is proportional to the fraction of the whole in each category. So as you can see right there, instead of just having like these charts, right, where they're stacked and like which ones, you know, oh, that one's the highest, that one's the lowest, which is kind of easy to see. This is when you're kind of comparing them. Like third class and crew seem to take up about a third each. And then second class and first class is that other third, but not quite. Okay, it gives you really good idea of how to like visualize the data and how they compare to one another. Okay, it's like crew and third class are similar, first class and second class are similar in size. It's really easy to read, I think, which we can kind of read that from here too. Okay, there are different ways to show the same or similar thing. A contingency table, okay, allows us to look at two categorical variables together. So if you have two categories that you're collecting data on, so for example, let's say I did a quick study with you guys. Maybe we'll do it in class today or when we have class next. Now, I've done this plenty of times in the past with my stat students, where I'll collect like two pieces of information. What's your gender? And do you have a driver's license? Okay, those are two categorical variables. Gender is a category, okay, categorical variable. And asking like a yes or no kind of question, like do you own or do you have a driver's license or do you not have a driver's license, right? That's like a yes or no answer. That's a categorical question too. And so you can make two like overlapping data sets that says like males with a driver's license, males without driver's license, females with a driver's license, females without a driver's license. Okay, and you can make this table to look at any possibly underlying patterns. All right. So as we see here, if you know anything about the Titanic, a very famous ship that sank, and not everybody survived, unfortunately. Okay. And this data is trying to see if there's any patterns that might stick out between maybe if you were part of the crew, or if you were, you know, maybe first class versus second or third class. Did everyone survive relatively the same? Meaning, did, like, let's say half the first class ticket holders and half the second class ticket holders and half the third class ticket holders and half the crew, did they all survive? Or did maybe one class of ticket holder or crew maybe have an advantage and maybe had a higher survival rate? Okay, these kind of patterns might not be clear unless you do graphical displays with them. Okay, so here once again, we notice from left to right, we have first class, second class, third class, and crew, and then alive or dead. And you notice there's totals on the bottom and totals on the sides, okay, or on the side. So you notice with alive and dead, they have total 711 people survived and 1,490 had died from the accident, okay, or disaster, or the wreck, okay. But for class, right, there was 325 first class, 285 second class, 706 third class, and 885 total. And then there's a total, which if you add left or right or up or down, it shouldn't matter. It's the same data sets, okay? You have 2,201 people were on the ship, okay? And then hopefully you're able to identify the first, second, third crew, whether they're alive or dead. Okay, it's important to be able to kind of read that information. So once again, as explained the margins, okay, we call it the marginal distribution. So if I said something about the marginal distribution of survival, you would say something like, well, the marginal distribution of survival would be there was 711 individuals that survived and 1,490 that did not. Okay, so more to that contingency tables, what we call a cell is that individual count that's a combination of the two values. So you have one category of class, right? And that, take like a crew member, for example. Well, you could also mix that with, like I said before, alive or dead, and then you have the individual cell of just that one item. So yeah, we knew there was 885 crew members, but 673 had died. Okay, so that 673 is like an individual cell that kind of we can look at and observe and compare to other cells. Okay. All right, moving on. This goes to conditional distribution. Okay, conditional distribution shows a distribution of one variable for just the individuals who satisfy some condition on another variable. Okay, the following is the conditional distribution of ticket class, conditional on having survived. So we're not looking at the entire table, we're just looking at the different classes, but the condition is you have survived. So in this case, we have a total of 711 people that survived. That makes up 100%, right? Because 100% of people that survived, there's 100% of them. Okay? Out of that, you could say, some statistics like, well, 28.6 that survived were in first class. 16.6 of those that survived were in second class. 25% that survived were in third class, and 29.8% of the total survivors, were crew members. Which that, sounds like a lot, right? 212 crew members survived. But knowing what we know from that data set, if you took a look at it a minute ago, we could also switch it up to the condition that they had perished, okay? They did not survive the shipwreck. So same kind of thing, right? You had 1,490 that had died from the wreck. So out of 100% of people that died, 8.2% were first, 11.2 were second, 35.4 were third, and 45.2%, that had passed away from the accident, were crew members. So as you notice, 29.8, almost 30% were crew members that survived, but almost 50% of people that died were also crew members. So that kind of shows you that the crew members were a large percentage of the overall people on the ship. All right. But this is like it's called a conditional distribution. So it's not just like a distribution, there's a condition to it, like first class people. But the condition is they survived, or the condition was that we're going to study was that they did not. Okay, it's called conditional distribution. It's like you start somewhere, then you move somewhere else. So more with that, conditional distribution tells us there is a difference in class for those who survived and those who perished. This is better shown with pie charts of the two distributions. So you notice these pie charts, the one on the left and the one on the right, both come from the same data set, right? The one we've been looking at. And you notice the green sections are first class, the pink are second, the blue or light purple is third class tickets, and then that yellowish color, orangish yellow, is the crew members. Okay, so on one side they're using the same data as from the previous two slides. Okay, this is where they're getting those numbers. You can see that those are not the same. Okay, when you see conditional distributions like this and they're put next to each other and you see that their graphs line up different, you know that there was a condition that had to be met that changed from one to the next. Okay, there was a dependence of something. Okay, so it seems like, not getting too much into it, but it seems like there was a dependence potentially, right? You don't always know, you weren't there, but there was a dependence of something, whether you survived or did not, depending on maybe what class you were or if you were a crew member or not. Okay, it seems like you might have had a higher or lower chance of survival depending on if you were first class, second class, third class, or crew member. If these were exactly the same, if those pie charts looked exactly the same, you couldn't argue that. You would say it didn't matter. Look at the charts are the same. Didn't matter first class, second class, third class, or crew. They were identical or very, very, very similar looking charts. Therefore, if there was any sort of like condition for survival, it didn't matter what class you were. Maybe there was something different. Okay, and that's just something I guess you got to investigate if that's where you were researching. Okay, so as I was mentioning before, we see that the distribution of class for the survivors is different from that of the non-survivors. Okay, it just look different. Look at this. Look at those two charts. They're different. This leads us to believe that class and survival are associated, that they are not independent. Okay, that they are dependent, that they have an association. That there's an association between what class ticket you had and if you survived. Okay, that's called not independent. That's called dependent. Okay, that there's a possibility that they're dependent. Okay, there's an association between the two things. The variables would be considered independent when the distribution of one variable in all contingency tables is the same for all categories in the other variable. Now, you might ask, or you might make a comment or a statement that it's very difficult for things to be perfect, right? Like, what if those pie charts, or what if those what do they call it, the distribution, right? What if they were just slightly different? What if it was like 1 or 2 or 3 or 5 numbers off, right? At what point would you call them independent, and what point would you not call them independent? So the general answer I like to use as a general starting point, okay, is usually about 5%. Okay, the number 5 you might hear a lot in this class for things like 5%, like 0.05. So if all of your values, so if we went back here and looked at all these values, okay, alive and dead, you see how it's 28.6 and that's 8.2, okay, 16.6 and 11.2, 25, 35, 29, and 45. If all of those numbers, when I paired them up like that, were off by like 5%, like let's say it said 28 and 27, like 16 and 11, 25, and let's say it was like, I don't know, 30. I'm just throwing some numbers out there, okay? But if they were extremely close, like all of them lined up to be only a few percentage points off of, like I said, no more than 5. For right now, I would say you would probably make a statement that says that it appears that they are independent. Okay, in this class in stats, a lot of times you don't want to use these black and white type words. You want to use those gray, fuzzy areas. Okay, like it appears that they're independent. Like it appears that they're from the data that we have that that appears to be like an independence between the two variables. Now, I'm using that as a blank statement. As you go into other math classes, other stats classes, like at college or beyond, you might hear something different, and someone could probably slap me and say, Mr. Atterbury, that number 5% you pulled out of nowhere. And I'll say, you're right, I did. It's a good starting point, though, okay? Generally speaking, you got to consider how big was the data set. Are you working with only 20 numbers, 100 numbers, 1,000 numbers, 10,000 numbers, a million numbers, okay? What's your data set? And generally speaking, the bigger the data set, the more numbers you have, the more you have to kind of like refine that and put it closer to 0, like a 1% or 2% difference, okay? Maybe even smaller than that. You might want to do a 0.1% if you have a huge data set, or it's a very sensitive topic that you don't really want to make any mistakes by saying something's independent or dependent and then causing chaos in the world, I bet. No, but seriously though, for now, independent versus dependent, we're looking at things to be within 5 percentage points of each other. So first class dead, first class alive, 28.6, 8.2. Telling you right now, they are not independent. Okay, like it's strongly suggests that it's not independent. That's probably the better way to say it. Like I said, keep it fuzzy, keep it kind of in that gray area. You're usually never going to kind of be wrong. I think I said that fuzzy also. Okay, but if those numbers, as you line them up, are super duper close, okay, like within 5 percentage points, and every pair that you match up is within 5 percentage points, you're generally pretty good. Okay, if they're all like 5 percentage points, maybe that's too much. But just for right now, use fuzzy words like suggest or strongly suggest or sort of suggest, things like that, independent or not independent, okay? If they look to be about the same, it's independent. If they're not the same, it's not independent. Independent, same, not independent, not same, okay? Okay, moving on. I think I beat that to death. I'm going to show you in another video later. I'll make one tomorrow or Tuesday. We'll go over how to make these segmented bar charts. We'll do a little activity. I love making these things. They're fun. Bust out the pencils, colored pencils, pens, okay, crayons. Why not? This is called a segmented bar chart. Essentially, you're taking these percentages, okay, and you're just stacking them up. Okay, as you notice, you have a first class, second class, third class, and crew. This one started with the first class on top. Usually how I do is I draw the big box, okay, and then I make little lines after I count up the percentage points. So this shows you there's about 30% alive of the crew, but about almost 50% alive or died from the crew. If you kind of look at your fingers and go, okay, it's about 10, 20, about 25% of the third class crew survived, but about 10, 20, 30, right? Almost 40. The third class tickets had passed away. So this is a great way to check the independence. Okay, segmented bar charts are an awesome way to check independence. If those two bar charts look almost the same, they're independent. Okay, if those bar charts like this one look different, they're not independent. Okay, once again, if they're the same, it's independent. If these look different, like these kind of do, it's kind of like the one on the left's kind of spread out, the one on the right's kind of like squished to the top. That is not independent. It's got to look a whole lot closer, okay? Once again, segmented bar charts. Note that using percentages is crucial. Percentages, okay? It allows us to compare groups of different sample sizes just by using relative frequencies, percents. Don't forget that. What can go wrong? Don't violate the area principle. You see that graph on the left? Don't do that. Don't do that. Don't do that. Don't do that, okay? It looks pretty. A lot of software lets you do things like that. Just don't do that, please, okay? Well, some people might think the pie chart on the left is better. It is harder to compare fractions on the whole, which a flat pie chart does so easily. Okay, please don't do that. It's so hard to kind of see it from this angle. Just don't do that. Make it easy. All right. Keep it honest. Make sure your display shows what it says it shows. So if you say something like, alcohol use is 50%, but you look at this table, this pie chart, and it's obvious that that's not cutting the circle in half, you've basically lost all credibility of your research or your study or your whatever by simply having like a bad looking graph that's just obviously bad. So don't do that, okay? Don't confuse similar sounding percentages. Pay particular attention to the wording of the context. For example, what percentage of seniors are males? And then what percentage of males are seniors? You see how those words are switched? Do you understand how they're different? So let's think about Serrano High School. Okay, what percentage of seniors are males? So if we have about 500 seniors, and I'm assuming about half are males, I'm going to assume about 250. The answer to that might be about 50%, right? So what percentage of seniors are males? I'm assuming, once again, about 50%. So I go to the next question, which looks exactly the same, but the words are just a little switched. What percentage of males are seniors? And once again, let's talk about at Serrano High School. If 50% of the school, okay, what percentage of males are seniors? I'm assuming we have a similar group number between freshmen, sophomores, juniors, and seniors. So what percentage are seniors? It's probably close to about 25%. Okay, it's probably close to about 25%. You see how the first answer was 50% because half of all seniors are males, or we're going to make the assumption right now. And about a quarter, or about 1/4, right, of males at Serrano High School are seniors. So the numbers are way off, 25% versus 50%. Might not seem a lot to you, but what if I said, hey, I just won $1 million. Do you want 50% or 25%? It's a big difference. It's a big difference, okay? And don't forget to look at the variables separately too. Examine the marginal distributions. It's important to know how many cases are in each category. So it says separate them. If you look at a table and there's two parts to it, right? You got to look at it one way and one the other way. You got to be able to separate the left and right from the up and down. Okay. Last but not least, okay. Don't overstate your case. Okay. Don't overstate your case. Don't claim something you can't. Don't use unfair or silly averages. This could lead to Simpson's paradox. So be careful when you average one variable across different levels of a second variable. Simpson's paradox is when you do a data set and you'll see these natural clusters that might have something similar, or the big pattern that comes out because you've got them in these little clusters, maybe by like ages or something. The best way I can describe Simpson's paradox is, let's say you're out at a soccer field for some little kid soccer game or something, or practice, and you go and you find the average height, okay, of all the people out at this game or practice. That average height might be like 4.5 feet. Okay. There might be people out there and no one is 4.5 feet. What's the issue? The issue is you have one group that's probably all over 5 feet, or, most adults are over 5 feet tall. And then you got, let's say, these little kids who are all about 4 feet, And so what you get is you get these two groups that have their own like thing, and so you want to study them separately. Okay, you want to kind of separate them. If you put them together as one big group, you might not actually see. It might make your data just kind of seem weird. So it's called Simpson's paradoxes. Okay, it's about unfair or silly averages. Sometimes you try to just group everything as one. Don't do that. Okay, sometimes you got to keep them into smaller groups. All right, that's it for chapter 2. Okay, going over the slideshow. It's probably a lot longer than I'm sure anyone wanted. Hopefully it kind of makes sense. Hopefully this helps you out understand the chapter, and I will see you in class, which will be online. All right, look for some more videos talking about how to draw some cool graphs and charts. All right, guys, have a good day.